Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're continuing along with my LTAM course. This time going over the problems from the SOA problem set list, problems 4.1 through 4.7. So, 4.1 talks about a special whole life insurance policy issued on a 40-year-old, and you're given that death benefits are payable at the end of the year of death. The amount of benefit is 2 if the death occurs within the first 20 years and 1 thereafter. They give you Z as the present value of payments under the insurance. They give you I, and they give you expectation of Z squared. And you want the standard deviation of Z. So first thing you notice about this is because the death benefit is piecewise defined, it's some amount for the first 20 years, some other amount thereafter. It's a Frankinsurance problem. Right? You just kind of Frankenstein's 2 different insurance arrangements together. You also notice that for a variance, variance is mean of the square minus square of the mean. They gave you mean of the square. You have to calculate the mean so that you can square it. Because it's Frankinsurance, you can say it's the same as an insurance policy for 2 the whole time minus a 20-year deferred insurance policy for 1. Right? That's how you get it to be 2 for a while and then drop down to 1. Crunch the numbers that they give you, gets you the mean. Variance is mean of the square, which they gave you, minus square of the mean, which you calculated. You get the variance. Standard deviation is square root of variance. And you get one of the answer choices. So again, notice that it's Frankinsurance, and use the fact that variance is mean of the square minus square of the mean. Next one. For a special 2-year term insurance policy on X, you're given that death benefits are payable at the end of the half year of death. The amount of the death benefit is $300,000 for the first half year and increases by $30,000 per half year thereafter. They give you QX and QX plus 1. They say to assume that deaths follow a constant force of mortality between the integer ages, and they give you the 2-year interest function. And ask you for the present value random variable for the insurance. Or sorry, they give you present value, and you want probability that Z is greater than 277,000. And so when you want probability that Z is greater than 277,000, what you do not do is something along the lines of find mean and variance of Z and use normal distribution, because there's not a large number of independent things here. You can't central limit theorem this. Instead, you realize that Z, the present value, is entirely dependent on the half year in which you die. So you have to look half year by half year and see which of them get you a value greater than 277,000 and which ones get you something less. Now, it is a 2-year term insurance, so you only have to look at 4 half years. But that part doesn't really matter. It could even be a whole life insurance because of what we find. For imminent death, Z is too small. For death in 6 to 12 months, it's big enough. 12 to 18 months, it's big enough. More than 18 months, it's not. And you'll realize because you're linearly adding stuff to the face value, but the denominator is growing exponentially, not linearly, once this Z value starts to decline, it will continue to decline. But ultimately what we want here is the probability of dying between 6 and 18 months. So to calculate the probability, you need probability of surviving half a year minus probability of surviving a year and a half. Because of constant force of mortality, that means for those half years you do square roots. Crunch the numbers just like you did in survival models. You get that for surviving half a year, it's 91.7% chance. A year and a half, it's a 73.7% chance. Take the difference, 18%. So again, don't fall for the trap of thinking that you can do mean and variance because it's not normal here. You have to look at which time periods the insured can die in and have Z be worth enough. Then you have to look at what's the probability of dying in those time periods, or in that one time period. All right. Problem 4. You're given Q60 using I equals 0.05. You're given A60 colon angle 3. If I were decreased to 0.045, calculate A60 colon angle 3. So you see a 3-year endowment insurance here. And at first it seems like you're one equation short in terms of matching your equations and your unknowns. Because you say, well, 3-year endowment insurance, that means I need to know about probability of dying in the first year, probability of dying in the second year, and probability of dying in the third year. Alright, so 3 unknowns there. You're given the total, so that gives you one equation. You're given probability of dying in the first year, but then you feel like you're one unknown short. You're actually not, because for an endowment insurance, it doesn't matter whether you survive the third year or not. Either way, you'll get paid 1 at the end of 3 years, or at the end of the third year. So to evaluate A60 colon angle 3, you actually only need the survival probabilities for the first 2 years. And that's how you tackle this problem. You notice that if I were to write out an expression for A60 colon angle 3, it would depend on the interest rate, obviously. And for the mortality, it would depend on the probability of surviving the first year and the second year. They give you the one for the first year, so if they give you the interest rate, you can use this to solve for the probability of the second year. Once you have both of those, you can change the interest rate. And that's the strategy. And here we implement it. We notice that A60 colon angle 3 is D60 over 1 plus I plus D61 over 1 plus I squared plus 1 minus D60 minus D61 over 1 plus I cubed. Again, I'm using this D notation assuming a radix of 1 at age 60. So that these are conditional probabilities of dying at that age, just conditioned on this policy being writable to begin with because you're 60 years old. So notice, we don't need D62, we just need D60 and D61. We're given A60 colon angle 3, we're given I, we're given D60, right, because D60 equals Q60. Solve for D61. Plug everything all back in using the new interest rate. We're at this 0.9732. It's just 1 minus D60 minus D61. And you get 0.8777. Next problem. For a special increasing whole life insurance on a 40-year-old payable at the moment of death, they give you a death benefit, they give you an interest discount factor, and they give you this probability of surviving T years and then dying. And you have to recognize that this TP40 times mu 40 plus T, that is F sub 40 of T. Right? You have to recognize that probability of surviving till some amount of time, and then probability density of dying. That is probability density of dying if you didn't survive till then. Or if you didn't necessarily survive till then, I mean. Right? So this TP40 mu 40 sub t, mu sub 40 plus t equals F sub 40 of t. You have to recognize that. And you want the variance of z. So variance is mean of the square minus square of the mean. Right. You should recognize that. And we just need our standard variance and expectations of stuff involving time-varying insurance. Right? Death benefit times discount factor times probability density of dying, all integrated over the appropriate region. Crunch the numbers, get an answer for expectation of z squared. So you square anything money related. Square the death benefit. Square the discount factor. Do not square the probability density. Crunch the numbers. Get something. And then you do variance is mean of the square minus square of the mean. So you have to square this value here. And there's your answer. So again, recognize that it's time-varying insurance. Set up the integral, right? One integral for just the mean, another integral for mean of the square. Hopefully you remember how to do an integral for mean of the square from exam P. And then variance is mean of the square minus square of the mean. Problem 4.5 was deleted because or was moved to a different chapter because it relates to something that they didn't think was appropriate for this chapter. But 4.6, for a 3-year term insurance of $1,000 on a 70-year-old, you're given Q standard ultimate life table is the mortality rate from the standard ultimate life table. Q70 plus K is the mortality rate used to price this insurance. Q70 plus K equals 0.95 to the K times Q standard ultimate life table. Fine. And they give you the interest rate. It says calculate the single net premium. Now, it's something I should have mentioned. And if this is why you can't do it, if you don't know what single net premium is, it's the amount that they would need to charge right from the outset. Rather than charging something every year, if they just charge some fixed amount right now, and then they pay you, it's a 3-year term insurance, so it'll pay at the end of the year if you die. How much would they need to charge for the expected present value to be 0? Again, so premium minus insurance benefit. Expected present value has to be 0. They have to balance out. If you are missing that piece of information and that's what was confusing you, feel free to pause the video and try this problem again now that you know what that means. But essentially, single net premium just means you need the net present value of the insurance benefits. And so yeah, we have to calculate this 1 year at a time. A 71st colon angle 3 equals D70 over 1.05 plus D71 over 1.05 squared plus D72 over 1.05 cubed. And sorry, D70 is just Q70 from the table. D71, you have to survive that first year, and then you're told that there's a 95% change in the, the death probability is only 95% of what the table tells you. And then for D72, you just multiply 1 minus D70 times 1 minus, I guess it should be 1 minus Q70 times 1 minus, 1 minus Q70 times 1 minus Q71, right? So that's what these get you. And then times 0.95 squared times Q72 from the table. Crunch your numbers together and you get the answer. Multiply by 1,000, you get that it should be $29.90. Lastly, you're given the following information from a life table. It gives you a partial table. They give you the number alive at 90 and the number alive at 93 and say deaths are uniformly distributed over each year of age. Calculate the probability that a 90-year-old dies between ages 93 and 95.5. Alright, so we know that the survivors to age 90 are 1,000. We know survivors to age 93 are 825. We just need to figure out survivors to age 95.5. Because deaths are uniformly distributed over each year of age, we need to find these two entries in the table and average them. So we have to start filling in the blanks in the table. Notice it says D97 is 72, but QX is 1, so everybody dies. So, if 72 people died, and everybody died, that means you had to start with 72 people. Then, at age 96, if you're told 20% of people from age 96 survived, and there were 72 survivors, crunching the numbers, you get that there had to be 36 survivors at age 96. Then you're told if 40% of people died from age 95, well, I guess what I should have filled in also is that this means 60% survived, so there would be a 0.60 here. You divide 360 by 0.60, you get 600 survivors to age 95. And once you have that, L95 is going to be halfway between, L95.5 is going to be halfway between L95 and L96. That'll be 480, halfway between 600 and 360. Crunch your numbers, you get Q90, 2.5 Q90 deferred 3 years is 0.345. Alright, so that's the first batch of problems. The rest will follow soon. As always, if you like the way I explain things and want to arrange private lessons, click the link in the description below. And until next time, this is Dr. Nighttime wishing you a good night.